Greetings everyone, my name is Nikos Charalampidis and today I'm going to present to you a novel chaotic map and its Taylor expansion Analogue. First, I'm going to start with an introduction and then I'm going to present to you the proposed chaotic map, then its Taylor expansion Analogue, and after that I'm going to show you a speed comparison which we did between the two chaotic maps by using a microcontroller. Finally, I'm going to finish this presentation with some conclusions and future research. First things first, what is chaos? In physics and mathematics, by chaos and chaotic systems, we refer to deterministic systems that showcase extreme sensitivity to initial conditions and parameter values. This means that if I were to compute the solutions of a system with almost identical initial conditions, these solutions would diverge from each other in a very short period of time. There are two major areas for chaotic systems. The first is chaos emergence in nature, with examples in engineering, meteorology, biology, astronomy, and basically in almost all physical phenomena. The second is chaos applicability, with examples in robotics, weather forecast, pandemic crisis management, circuits, and information security. In particular, in the discipline of information security, there are many advancements in the field of chaos-based cryptography with ubiquitous applicability. For example, in random bit generators, watermarking, hazing, secure communications. The determinism, the dubious behavior, and the low computational cost of chaotic systems provide an excellent foundation for implementing a plethora of encryption schemes. But most works limit their study on numerical simulations performed on a computer. However, recently there is an ongoing effort to efficiently implement chaotic encryption designs to build upon their commercialization potential. So, inspired by that, we decided that we also want to design a chaotic encryption scheme implemented on microcontrollers. So we started by designing a chaotic map. And as you can see here, we considered a chaotic map that is comprised by the exponential function, the sign map, and modulo map. As you can see from the bifurcation diagram, this map exhibits large region of constant chaos, and from the phase diagram you can see that it has also an indistinguishable phase portrait. And from the last two figures, you can see that the Lyapunov map is able to achieve high Lyapunov exponent values. So this map exhibits complex behavior and is at first well suited for encryption schemes. However, when we decided to move forward with this map on microcontrollers, we realized that its complexity and the high computational cost, because we have to compute the sign map and also we need to compute the exponential of that. Results in slow encryption and decryption algorithms. As a result, this chaotic map is less user-friendly and complex to implement in embedded devices. That is why we decided to move forward with its Taylor expansion analog. As you can see, again, the Taylor expansion analog of the proposed chaotic map has again constant chaotic behavior, indistinguishable phase portrait, and as a matter of fact, is able to achieve higher Lyapunov exponent values than the Lyapunov exponent values of the proposed chaotic map. And we claim that this Taylor expansion analog map of the map is less computationally complex and faster. And why we say that? Because, as you can see in equation 2, there are e to the power of a, we only have to compute it once. And then after that, we have it for every next iteration. P times r, again, we only have to compute it once. 1 over 2 times pi square r square, we only have to compute it once in the beginning. 1 over 6 pi to the power of 3 times r squared minus 1, again, this also, we only have to compute it in the beginning. So every iteration after that boils down to 6 multiplications and 3 summations. So with that logic in mind, we decided to test it. And not only test this map, we also tested the original map and we compared them. We produced 100,000 bits and we saw that while the original map takes about 5.41 seconds to produce 100,000 bits on an STM microcontroller, the Taylor expansion analog of this map takes 2.32 seconds. This means basically that the Taylor expansion analog of the map is at least twice as fast than the original map, which makes it a very good candidate to continue with implementing implementations of encryption schemes on a microcontroller. And also you can see here that the machine cycles per iteration of the original map are at least twice as much as are the ones in the Taylor expansion analog. So, to finish our presentation, we have presented to you a novel chaotic map based on the exponential function, the sign map, and the modulo operator. And this map exhibits large regions of uninterrupted chaos as well as highly Lyapunov exponent values. Then we introduced you the Taylor expansion analog of our map, and as it was expected, again, the Taylor expansion analog has large regions of uninterrupted chaos, highly Lyapunov exponent values, and as a matter of fact, the Taylor expansion analog of our map showcase higher Lyapunov exponent values than the original counterpart, which basically means that it has a more complex behavior. And then finally, we showed you a speed test comparison between the two chaotic maps on a low-cost STM microcontroller, which basically showed us that while both maps are appropriate for encryption schemes, the Taylor expansion analog is a better fit for implementation on embedded devices. So the next thing we are going to do is take this Taylor expansion analog map and apply it to real-time speech encryption embedded system. Thank you very much.